Have you ever stopped to think about what's really going on inside your phone or your computer? In that silent, invisible world. Well, today, we're going to take that journey. We're going to find the one single process that makes literally everything you do possible. No, seriously, think about it for a second. You click your mouse, you tap your screen, you swipe, and boom, a lightning-fast chain reaction kicks off deep inside the machine. So let's follow that reaction step by step and see exactly where it goes. Okay, so right at the heart of this whole thing is one super critical component, the central processing unit. You know it as the CPU. And calling it the brain of the operation, that's not an exaggeration at all. It really is. So this little chip, the microprocessor, it's the ultimate workhorse. I mean, every single instruction, every little piece of data has to go through it to get processed. And it doesn't matter if we're talking about a giant supercomputer or the phone you've got in your pocket. This one chip is running the entire show. Now, you'd think that every computer out there is totally different, right? But what's wild is that almost every single one of them, since way back in the 1940s, follows the exact same fundamental design. It's this master plan that was so good, so effective, we're still using it today. And here it is. This is the von Neumann architecture. The real genius here is just how simple and elegant it is. See, you've got the CPU, that's our brain. Then you have one single spot for memory, and this is key. It holds both the instructions and the data together. And connecting it all are these buses, which are basically just superhighways for information. This simple blueprint, it's the foundation for pretty much all modern computing. Incredible. All right, so if we zoom into the CPU itself, there are two main players. First up, you've got the control unit. The best way to think of it is like the ultimate traffic cop. Its job is to grab instructions from memory and then direct all the traffic, all the flow of data, telling every other part of the computer exactly what to do and when to do it. It basically synchronizes the whole show. And the second key player? That's the arithmetic and logic unit, or ALU for short. So, if the control unit is the director, the ALU is the genius mathematician. This is the super fast calculator that's doing all the math, addition, subtraction, and all the logical decisions, things like and or. This is where the real number crunching gets done. So how do these two parts actually work together? Well, they follow this constant repetitive rhythm, a really simple three-step cycle that is, for all intents and purposes, the actual heartbeat of your computer. And this flowchart right here, it maps out that heartbeat perfectly. It's called the fetch, decode, execute cycle. And this is the journey that every single instruction takes. I don't care if it's open a file or fire a laser in a video game, it has to go through this process. The whole entire journey boils down to just these three crucial steps. It's beautiful. First, the CPU fetches an instruction from memory. Simple. Second, it decodes that instruction, to figure out what it's supposed to do. And third, it executes the command. That's it. Fetch, decode, execute. Over and over and over again. Okay, and here's the part that just blows my mind. This isn't happening like once or twice a second. When you see a CPU advertised with a clock speed of, say, 3.5 gigahertz, what that actually means is that this three-step cycle is running 3.5 billion times every single second. That incredible speed is what makes everything we do on our computers even possible. So to work that fast, billions of times a second, the CPU just can't afford to wait for data to travel all the way from the main memory and back again for every little thing. It's too slow. So it needs its own tiny, ultra-fast memory right there on the chip, and these are called registers. The best analogy, just think of them as the CPU's personal sticky notes for jotting things down really quick. All right, let's look at the key players here. You've got the program counter, or PC. That's like a bookmark, always pointing to the next instruction in line. Then, for moving data, you've got this great team, the MAR and the MDR. The MAR holds the address of where to go, and the MDR is where you temporarily store the actual data you get from that address. And finally, the current instruction register, or CIR, is holding the one instruction that's being worked on right this second. And this image shows you exactly how they work together. It's brilliant. So, to read something from memory, the CPU puts the address it wants into the MAR. You can see it at the top there. The memory system goes and finds that exact spot, and then it copies whatever's there into the MDR at the bottom, ready for the CPU to use it. It is just a beautifully efficient system for getting data where it needs to go, fast. Okay, so now that we get this cycle, Let's zoom out a bit, because this exact same process isn't just humming away inside your laptop. Oh no, it is happening all around you, right now, in places you probably never even think about. We call these hidden computers embedded systems. They're basically specialized computers, a lot of times just a single little microcontroller chip designed to do one specific job and one job only. But, and this is the cool part, deep down, they are still running that exact same fetch, decode, execute cycle we just talked about. A modern car is the perfect example of this. You think of it as one machine, but it's not. It's a whole network of dozens of these little computers. You've got a separate embedded system for the engine, for the anti-lock brakes, for the airbags, the entertainment system, you name it. And they're all constantly talking to each other. Or hey, what about a vending machine? Seems simple, right? But at its core, there's a microcontroller running the show. When you press that button, it's fetching an instruction. It decodes your choice, it checks if you put in enough money, and then it executes the command to turn that little spiral motor and drop your snack. It's the same exact principle, just for a much tastier purpose. Now, there's a reason we use these little guys everywhere. The benefits are pretty obvious. They're small, they're cheap to make, they barely use any power, and they're incredibly reliable for doing one thing over and over. But there's always a but, right? The trade-off is they're a pain to upgrade or fix, and once a device they're in is obsolete, they often just become e-waste. So next time you pop something in the microwave, or start the washing machine, or even just turn on a smart light bulb, take a second to think about that invisible world buzzing away inside. That constant, simple, powerful rhythm, fetch, decode, execute, running billions of times a second. That's what's powering our entire modern world. It really makes you stop and wonder, doesn't it? Just how many of these little computer brains have you already used today?